Just finishing up the section with some more vocab. We have trend line, interpolation, and extrapolation. That's how you pronounce that. And a trend line is that line that we put into our scatter plot to model the data. So, the definition I'm going to put down, I mean, we've drawn trend lines already, but the definition I want to put down is the line that we put onto a scatter plot. The line we put on a scatter plot. And the reason that we put that line on the scatter plot is so that we can model the relationship. So the line we put on the scatter plot to model a relationship. When I say to model a relationship, what that means is we put the line on there so that we can come up with an equation. And that equation is the model. So if it says create a model, it means put a trend line on there and then write an equation for it, just like we did on that little project. Interpolation is once you've found the model, so you put your trend line on there, you come up with the equation using your two ordered pairs that you found. Then interpolation means that you use the model to find an estimate within the data. So like I have a data set, and maybe that data set was the feet length and the height of everybody in the room. If I were to say somebody else that was sort of within that data set, so like the smallest foot that we had was 20 centimeters, and the biggest foot that we had was 30 centimeters, somebody who falls in that data set would have a foot that is between 20 and 30 centimeters. Okay? That's using interpolation, because the extra piece of data or the estimate that we're trying to find falls within the data set that we already have. Extrapolation uses the model, so use the model to predict a value outside of the data. And on that foot length versus height thing that we did, when we found out my height, I was outside of the data because I'm way taller than everybody here and my foot is longer than everybody here. So the data point that you guys found for me, my foot length, was outside of your data set, which means that what we did was extrapolation. We predicted my height based on the data that we had. Because we had to predict it, my foot length was outside of the data that we had. Okay, so how to model data using a line of fit. We've already done it on that project, so hopefully all of this makes sense. First, make a scatter plot and determine the correlation. So let's say I've made this scatter plot and I have some data that looks like this. What's the correlation here? Positive correlation. As the x variable increases, the y variable increases. Okay, so that's the correlation. Now, if there is a correlation, this is huge right here. If there's a correlation, if there's not a correlation, if you say no correlation, then there's no line to draw. You can always draw a line anywhere on anything, but that doesn't mean the line has meaning. There has to be a correlation for it to have meaning. So, if there's a correlation, then draw in your line of fit. So, on my little sketch here, I'll draw in a little line so that we can kind of see what I'm talking about. There we go. That line right there is called a trend line. That's this line right here. The line we put on a scatter plot to model a relationship. So I'm saying that this trend line right here kind of matches up with the data that I put on all those dots. Okay? Now, the line should pass as close as possible to all the points. Does my line kind of look like it passes close to all those points? Kind of, yeah. The line does not necessarily need to go through the original data. Does my line go through the original data in any way? Sort of, maybe. I mean, like right here, maybe that line is crossing that dot, and maybe up here the line is crossing that dot, but that's a coincidence. I didn't intentionally make the line cross through any of my data, okay? So that's what that second one is there. Does not necessarily need to go through the original data. And then finally, try to make the line go through some easy points. Now, I'm not saying make the line go through your data. I'm saying if you have a grid on here, which you will have a grid when you're trying to graph, try to make the line pass through a couple of easy points. And we said last time, when I was explaining how to draw a line when we were working on that project, that my dots should be, what, close together? As far apart as possible. So I'm looking for, hopefully, some sort of dot or some sort of part of my line in that region and something on my line in this region that crosses over some sort of grid line so that I can easily pick out the ordered pair. I don't want to pick two dots that are close together. Maybe two dots down here, or two dots here and here, or two dots up here. I don't want close together dots. Because if my guess or if my line that I draw is off by a little bit, which it will be, then that little bit of line being off is going to cause me to have hugely wrong slopes and y-intercepts. So you want to make sure that your dots are far apart to kind of minimize that error. Okay, number 3, use 2 points on the line of fit, not from the original data necessarily. If your line happens to go through a couple of original data dots, then great, use those original data dots. But it does not have to. If it doesn't go through any of your data, then you want to find 2 points that are on that line, and then you can completely ignore everything else. Then, once you have those 2 points, you can write your equation for the line of fit. In order to do that, if you have 2 ordered pairs, what's the first thing you're going to do? 2 ordered pairs, I want to write an equation. What do I need to do first? Find your slope. So, find slope. Then what? Plug it into, what's the equation that we're going to use? Y minus y1 equals m times x minus x1. What's that one called? Plug into point slope form. And then once you have that written down, what are you going to do? Solve for y. So then put in slope intercept form. So the process is fairly straightforward. Once you have your scatter plot and you draw on the trend line, you pick 2 points on the trend line. Once you have those 2 points, find the slope, take your slope that you found, and one of your ordered pairs, plug it into point slope form. And then once you've done that, put it in slope intercept form. And then you have the equation for your line. Then, step 4, use the equation to make predictions. Once you have that equation, you can find any answer you want. I can give you some sort of question like saying, how tall will a person be if their foot is 20 inches long? And then you can use your equation to figure that out. Interpolations or extrapolations. How tall would a person be if their foot was 22 centimeters tall? That one fell within our data set. That would be an interpolation. Okay, the table shows the largest vertical drops of 9 roller coasters in the United States and the number of years after 1988 that they opened. Identify the independent and dependent variables. Is there a relationship in the data? If so, predict the vertical drop of a roller coaster built in 2013. How far does our data go? How many years does our data go? It goes 15 years since 1988. So what year is that? So 1988 is here. What year is this? 1989. What year is this one? Years since 1988, so that would be 91. Years since 1988 is 5 now, so that's 93. Years since 1988 now is 8 years, so 96. And then this one? That is 2000. So this one is also 2000. This one is also 2000. What's this one? 2001. And this one's 2003. Okay? So these roller coasters have this vertical drop here in feet. 151 feet here. That was like the tallest roller coaster in the world or something at that point. And then we started going up from there. All the way to 2003, they made this roller coaster that had a vertical drop of 400 feet. That'd be fun. I've been on it. Sure. So we need to decide which variable is the independent variable, which variable is the dependent variable. Which one is it? Which one probably causes the other to change? Years. As years goes by, what seems to be happening to the heights of the roller coasters? The heights are going up. So this one seems to be the independent, and then this one is the dependent. Okay, so that means that which variable will I call, or which one of these will I give my x variable to? The years. Independent variable is your x. That's your x-axis. So that makes this one y. Okay, now I'm not being very creative. I could have chosen like t for time and v for vertical drop, but this is going to work just fine. Okay, now do we have negative time? Do we have negative heights? No. So I can put my axes here. And because of the way that I've labeled stuff, what's going to go on the x-axis? Years. But it's not just years. It's years since 1988. Notice that because we're going on years since 1988, it's very easy numbers here. That's kind of an important thing. Otherwise, we're down here right in 1988, 1989, 1990, blah, blah, blah. So that's why we go with stuff like this. So I need to go from 1 all the way to 15. I have 14 lines. Will that be okay? Yes. So I can just go by ones. So here's 1, 2, 3, 4, here's 5, 6, 7, 8, 9, 10, and then 14 over here. 15 will be slightly off my graph, but it's just a scatter plot, so that's kind of okay. Now for the vertical drop, we have, what's the lowest number we have? 151. What's the highest number? 400. So if I started down here at 150, I got to make it to 400. How far is that? How much more is that? Sure. If I started 150 down here, if I go by 25s, I got to make it all the way to 400, right? That seems like it'll probably work. So if I go with 150 there, and then by 25, then I got 175, here's 200. 25, 50, 75, here's 300. 25, 50, 75, here's 400. Okay, that seems like a pretty good scale there. So let's go ahead and put those dots on there. So here's the graph based on the scale that we came up with. Does it look like there's a correlation here? Kinda, yeah, sure. So because we spread the scale out so much here, it kind of looks like, I don't know, maybe we're kind of a little bit loose here, but that's okay. If I were to squeeze the scale down, then I would start to see dots that go like that, okay? So the more you spread the scale out, the looser the dots are going to look. The more you keep the scale compacted down, then the tighter everything's going to look. It doesn't mean you want to keep the scale squished down. You do want it to be sort of spread out on your grid, okay? It does look like we have some sort of graph that we can put on here. So I'm just going to do the best that I can to draw in a trend line that sort of matches the data. What do you think? Somewhere in here? Maybe? It's kind of hard to say. Somewhere maybe like that more? I don't know. Okay. I know you can't see that in the video, but so there we go. There's my line. Now in this case, can I go below the x-axis? I can. On this graph, I broke the graph right here to make that 150 on my scale, and that's why breaking the graph is dangerous. Starting down here at 150 makes you think that you got a y-intercept somewhere in here, maybe like 140 or something like that, but that's not true because I broke the graph, all right? You can't talk about the graph if you break the graph. You can come up with a couple dots on your line and come up with the equation for the line, and then you can talk about y-intercepts from the equation, but you can't just by looking at the graph because of that break. So be careful about breaks. All right. Identify the independent and dependent variables. We did. Is there a relationship in the data? Answer that question. Is there a relationship here? Yes. This is a positive correlation. Meaning as years go on, these roller coasters seem to be getting taller. Okay? All right. Now, if so, predict the vertical drop in a roller coaster built in 2013. That means we have to come up with our equation. So what we're going to have to do now is pick 2 points that look like they're pretty good points on our line. So on here, I'm looking for where my line crosses grids exactly. Ooh, there's one right there. That's a good one. For my line anyway. And then somewhere down here, maybe right there, pretty close. Okay, your lines, you're probably going to have different dots, and that's okay. Now for me up here, I'm going to ignore what you guys have, and we're just going to go off of this, for me anyway. So I want to figure out what those ordered pairs are. What is this ordered pair, this first green dot? Looks like 4, 200. And then this green dot right here, what do we have here? 13, 350. So that's just for me. Now your graph, your line is going to give you different dots, but it's probably going to be fairly similar to what I have. Now the next thing we have to do is calculate the slope. We do that from the 2 ordered pairs that we have. As soon as we have these 2 ordered pairs, the scatter plot is completely irrelevant. We don't need it anymore. All we care about is those 2 ordered pairs. So M equals y2, which is 350, minus y1, which is 200, divided by x2, which is 13, minus x1, which is 4. So I have 350 minus 200, which is 150. And I have 13 minus 4, which is 9. That reduces. If I divide everything by 3, then I wind up with 50 over 3. So what that means is roller coasters are gaining 50 feet in height, based on my graph, every 3 years. So every 3 years that goes by, the roller coasters that are being built are 50 feet taller based on this model. Okay? So now we want to come up with an answer for the problem, which means we need to write our equation in point-slope form. So point-slope form is y minus y1 equals m times x minus x1. So y minus, which ordered pair looks easier? Yeah, I agree, 200 or 4, 200. So it's going to be y minus 200 equals my slope, 50 over 3, times x minus 4. All right, so we have y minus 200 equals 50 divided by 3x minus 200 divided by 3. Now on these types of problems, you can go to decimal, round to 3 decimal places, that'd be fine. So y minus 200 equals, what is 50 divided by 3? Like 16.6 repeating? It's a guess. Press Control Enter on your calculator. What do you get? $16.6 repeating. Okay, so I write 16.67 x minus, what's 200 divided by 3? 66.6 repeating. Okay, 66.67. Okay, just solve for y. We add 200 to both sides. So add 200 to your negative 66.67, and you get y equals 16.67x plus 133.33. Right? I hope. Okay, so this is our equation now. This is my equation. If you were doing this on your own, your equation might look a little bit different, and that's okay. So now we want to predict. It says predict the vertical drop in a roller coaster built in 2013. So what are we going to do with that 2013? We're going to plug 2013 in for x right here? Or are we going to plug in for y? What is year 2013? Which variable is that? That's x. Years, but it's years since 1988. So if 2013 is in here, then how many years since 1988 is that? It's 25. So we're going to plug 25 into our equation because we're using years since 1988. So I write y equals 16.67 times 25 plus 133.33. Enter all that into your calculator. What do we get? $550.08 what? So feet. Don't forget your units. So in 2013, based on this model, we should have seen, since it's not 2013 anymore, we should have seen a roller coaster that was 550 feet tall, based on this model. Okay? Now, did that happen? I don't know. But the model says that this is what would have happened using this data right here. And that is the answer to the question. Whether it happened or not, doesn't matter. That's the answer. The next time that Old Faithful is going to erupt actually can be predicted using how long the current eruption goes. So next time you go to Old Faithful, you could time it. The first time you see a little bit of water come shooting up from Old Faithful, time it until you see that last little drop of water come shooting up out of Old Faithful, and that time can be used to predict the length of time it will be until the next time that Old Faithful erupts. That is how, when you go to Old Faithful and you go into the pavilion and you see the little thing that says next eruption will occur around like 2:15 p.m. or something like that, that's how they do it. They use this right here. That's why Old Faithful is called Old Faithful, because somebody figured out that if you time the eruption length, that can be fit into a mathematical model to tell you how long it's going to be until it erupts again. It won't tell you how long the next eruption is going to last, but it will tell you how long it's going to take before the next eruption will occur. Okay? It's kind of a really interesting thing. And that is how they predict it. Okay, so we have duration. This is how long Old Faithful erupted for. And then we have the interval. How long until the next eruption. So which variable is the independent variable here? Which one makes the other one change? The duration. makes the interval until the next eruption change. So identify the independent and dependent variables. Duration is the independent, and interval is the dependent. And make sure you understand what duration means and what interval means, because both of those are kind of saying the same thing. The units are both minutes here. Okay? What do you want to call duration for a variable then? X. That's the independent variable, and which makes the interval until the next eruption y. Now I don't have negative time in either case, so I'm going to put my axis in the lower left-hand corner. On the bottom axis is going to be duration, and on the vertical axis will be the interval. Now for duration, we have 1.5 all the way up to 5. Yeah, we could go by halves, that'd be okay. So by 0.5. So that makes 1, 2, 3, 4, 5. Then we have the interval. And the interval, the lowest number is 48, and the highest number is 100. We have 14 lines here. Because of the fact that these numbers are small enough, and we have 14 lines, I could go by tens and be starting at 0. And that's what I'm going to do. If I can avoid breaking a graph, I will avoid breaking a graph. So I'm going to go by tens here. So that's 10, 20, 30, 40, here's 50, 60, 70, 80, 90, here's 100. All right, now we just plot those points, so let's go ahead and do that. So this is the graph here, my scatter plot. The dots are nice and spread out. They're not all squished into a little corner over here, so this is pretty good, okay? You don't have to have dots starting down here and ending all the way up here, or starting all the way up here and ending all the way down here. But you do want it to be kind of spread out so that you can start to see the pattern. All right, does it look like we have a relationship here? Yes, most definitely. This is actually a stronger relationship than the last one that we did. If I compare the two, the last one had dots all over the place. This one has dots that almost fall exactly on a line, and that is completely true of Yellowstone's Old Faithful. This is actually what happens. So I can draw in a line, and what I'm going to do is, as I put my meter stick on the board, I can see that my line actually is going to pretty much go through the majority of those dots. So I'm going to do my best to draw my line to actually land on these two ending dots. The reason that I'm doing that is because now that my line is ending on these two dots here, I can use those specific ordered pairs to generate my equation. This dot right here, or maybe I can use that dot right there, it makes no difference. But this dot right here, or maybe this dot right here, you can use either of those. They're nice and spread out, and I intentionally made my line go through those dots so that I could do that. It saves me a little bit of effort. So let's say I'm going to use this one right here. That's this guy. And maybe I'm going to use this one right here. That's this guy. So now I have my two ordered pairs already. It's 2, 55 here, and 5, 100. So what do we have to do now? Find your slope. M equals what? y2 minus y1. So 100 minus 55 divided by 5 minus 2. So 100 minus 55 is 45. And 5 minus 2 is 3. 45 divided by 3 is actually 15. So what this slope means is that's 15 over 1. The y value is the amount of time until the next interval. The x value was the duration, how long it erupted for. So what this means is for every minute, this is 15 over 1, for every minute that Old Faithful erupts, 15 minutes will go by until the next eruption. Okay? That's what that slope means. Now we can write our equation. So what will I have? Okay, we're using this ordered pair here. That's fine. Y minus 55 equals x minus 2. Okay. Now we put that in slope-intercept form. So we distribute y minus 55 equals what? 15x minus 30. And now we solve for y, which means we have to, good, plus 55 to both sides. And my equation is y equals plus 25. So there's your equation. Now, let's make sure we're answering all the problems here. Draw a line of fit. We did. Write an equation for your line of fit. We just did. Then it says use your equation to predict the interval to the next eruption for a 7.5 minute eruption. So what are we going to do? Plug in 7.5 for x. So we have y equals 15 times 7.5 plus 25. Enter all that into your calculator. What do we get? It's around like 140, I think. 100 what? Oh, 137.5 what? Minutes. How long is that in hours? Yeah, it's a little over 2 hours. There's 120 minutes in 2 hours. So it's like 2 hours and 15 minutes. This is what they'll do. They have this equation sitting there. Somebody just sits there, and every time it erupts, they just press a stopwatch, because there's people working there all the time. They just hit a stopwatch, and they watch it erupt, and when it stops, they hit the stopwatch, they look at it, and then right here, they plug it in, and they come up with an answer, and then it's immediately, like in a matter of 10 seconds, they'll change the sign to tell you what time it's going to erupt again. It's that fast with this mathematical model. It's pretty cool. Okay, so that's the answer for part B. Now part C, can you use this equation to predict the length of the next eruption? This equation predicts how long until the next eruption. It uses the current eruption time. Does it have anything to do with the next eruption time? No. We can't predict how long the next eruption is going to last. But we can time the next eruption and then predict how long until the next eruption after that. Okay? That's all this equation does. Will it predict how good the eruption is going to be? Like sometimes you see it go off and it's kind of lame. Sometimes you see it go off and it's huge, like bigger than you've ever seen before. Can we predict that from this equation? No. All we can predict is how long until the next one. The last little piece of this section has one or two more vocab words. The first one is causation. Causation. That's basically the word cause is in causation. Do you see that? Okay. So causation means that something basically causes something else. Something causes something else to happen. Kind of like independent variable controls the dependent variable. This is the same kind of idea. So determine whether a relationship has correlation. Then if the relationship has correlation, determine whether or not the correlation is causal, not casual. Okay? These are two different words. This is causal, this is casual. Notice the difference. The U and the S are in their different spots. Okay? Causal is causation. Does one cause the other to happen? There can be a relationship, but does one directly cause the other one to occur? Okay, so the number of loaves of bread baked and the amount of flour used. Are those two things related? Yeah, because to make bread, you got to use flour, right? Okay, so this is a correlation. So determine whether a relationship has a correlation? Yes. Is the correlation causal? Does one cause the other to happen? Uh-huh. Okay. Let's skip causal for a second. The number of mailboxes in a city and the number of firefighters in that city. Would there be a correlation? If I have more mailboxes, then what is true about my city? There's more people. If there's more people, that means that the city is probably bigger. So the more mailboxes I have, the more population there is. Would I therefore need more firefighters? Yes. So there is a correlation. But do the number of mailboxes cause me to have more firefighters? No. So not causal. Okay, now that we understand that one, let's go back up here. The number of loaves of bread baked and the amount of flour used. Yes, there is a correlation. Is it causal? If I bake more loaves of bread, does that cause me to use more loaves of flour? Or more cups of flour, sorry. Yes. So yes, causal. Okay, how about the third one? The cost of a family's vacation and the size of their house. Yeah, if you have more money, do you probably have a larger house? Yes. So, if you have more money, are you likely to spend more money on a family vacation? Yes. So if I were to graph the size of people's houses compared to the amount of money they spend on vacations, would I see a correlation there? Yes. So yes, correlation. But does the cost of your vacation depend on the size of your house? No. I could go out and spend $30,000 on a vacation and still have a smaller house than somebody else who has an enormous house. And they spent way less than I did. So causal? No. How about the time spent exercising and the amount of calories burned? There's definitely a correlation. What about causal? If I exercise more, does that cause me to burn more calories? Yes. So yes to both on that one. And finally, the color of a student's eyes and the height of the student. No correlation. So therefore, we don't have to say anything about causal or not. And the last thing we need to do is called line of best fit. So I made a trend line. I made a couple trend lines up on the board. And you guys did exactly the same thing with the trend line that you had, the data that you had. You put a line on there. Was your line the same as my line? Was your line the same as anybody else's line? No, probably not. So that means that we had like 15 different trend lines for the same data. Well, who was right? All of you were right. Even though everybody came up with a different equation and everybody came up with a different answer, everybody was right, more or less. Okay? Well, there must be a line that works the best. The one that works the best is called the line of best fit. So the trend line that models the data perfectly. All of us were close, but none of us had the exact perfect trend line. The correlation coefficient is a measure of how accurate the trend line is. Okay, so the correlation coefficient, we'll figure out what that is later on. But the correlation coefficient basically just determines how strong the relationship is. So I'm going to put that on there too. So now we know that there is a perfect trend line that we can come up with. We will use computer programs. So your calculators will do this. Excel will do this also. When you use a calculator or Excel, it will give you the perfect trend line using the data rather than just a guess, which is what we were doing before. So we're almost out of time here, so I'll have to do this another time. Use Excel to enter the data into a spreadsheet and have it generate the line of best fit, the equation, and the correlation coefficient for the Old Faithful problem. So we'll go back next time and we'll look at the Old Faithful problem again using a computer or calculator to calculate the actual line of best fit. And then once we have that equation, we can use it to predict the interval of eruption, the 7.5 minute long eruption again, and then we'll compare this answer to the answer that we're going to get. So that's for next time.